Welcome to Master Prodigy. My name is Rulof, and in this video I'll be giving you an introduction to math and science. I'll be talking about the subfields of mathematics, physics and chemistry, and the importance of all these fields, and how they are used in engineering to improve our daily lives. So let's get started. Since humans first arrived on the scene, they found it convenient to use numbers for counting. Soon they started adding, subtracting, multiplying and dividing numbers with each other for everyday purposes. The field of mathematics quickly grew in complexity as time went by. The people that developed new and more extensive mathematics usually did so simply out of curiosity and to experience the elegance that lies within. Even though these early mathematicians were all inspired by the art and beauty of what they created, there was usually nothing useful about the math. It was usually only until much later when some mathematician or scientist found a use for the mathematics to solve a real-world problem. Pure mathematics can broadly be categorized into four sections. These are number systems, structures, geometry and calculus. Number systems is the study of numbers. It starts with natural numbers and performing arithmetic operations on them. Then it looks at integers, which also contains negative numbers, and real numbers, which has an infinite decimal point, as well as complex numbers, and several others. Some numbers like pi and the exponential has some interesting properties. You can then start taking numbers in the form of variables and plug them into equations. This is where the subfield of structures originates. The rules of how to manipulate these equations are contained in algebra. Included in structures are vectors and matrices, which are multidimensional numbers, and the rules of how they relate to each other and how to manipulate them are contained in linear algebra. The next area of mathematics is geometry, and it studies different kinds of shapes. Then it looks at space, which these shapes, or certain combinations of shapes, occupy in the form of areas and volumes. The Pythagorean theorem, which was developed by Pythagoras, determines the geometry of a right triangle. Closely related to the Pythagorean theorem is trigonometry, which also determines the geometry of a right triangle. The final area of mathematics we are considering here is calculus. Calculus is the study of changes. It looks at the slope of functions, which can be determined with differentials, and it also looks at the area under functions, which can be determined with integrals. And those are the four areas of mathematics we are considering. It should be noted that these four areas are very closely related. These areas can also be combined. For example, calculus can be performed on vectors, and the resulting field becomes vector calculus. And trigonometric functions can also be integrated. If you delve deeply enough into one area, you will eventually require knowledge of other three areas as well, since these four areas are all connected to each other. Pure mathematics can be used to solve real-world problems. When this is done, it becomes known as applied mathematics. Physics has a very close relationship with mathematics. Mathematics is like the language of physics, and you can't have physics without mathematics. Now we delve more deeply into physics. Physics can broadly be broken down into three areas. These are classical physics, relativity, and quantum physics. When we study physics, we start at the basics of classical physics. Isaac Newton was a genius that figured out how force and motion is related to each other and how gravity works on objects. To this day, Newton's laws of motion and his law of universal gravity is used to get rockets and satellites into orbit. Classical mechanics is very closely related to Newton's laws, and it describes the motion of solid objects when forces are applied to them. For example, gears turning in a gearbox of a car. Where classical mechanics describes the motion of solid objects, fluid mechanics describes the motion of fluid, such as water flowing through a pipe or air flowing around a moving car. Waves is the study of how energy is transferred through a medium, for example, a distortion traveling through a guitar string, ripples moving across a water surface, and sound traveling through the air. Optics is very closely related to waves, since a light beam is basically a wave. Light is however different from normal waves, since it doesn't require a medium to travel through. Light can travel through the vacuum of space, but it still follows the same principles as normal waves. The study of optics allowed us to construct microscopes, to examine the very small, and it also allowed the construction of telescopes, to examine the very big in outer space. Electromagnetism is the study of magnetic and electric fields. A changing magnetic flux can induce an electric field, and a changing electric flux can induce a magnetic field. This forms the basis of electricity and electric circuits. Thermodynamics is the field that describes energy and how it can be converted from one form to another. It also includes entropy, which is a measure of disorder in a system, and it can tell you how useful different kinds of energy are and how effectively it can be converted from one form to another. Next, we move to relativity. The genius who developed the theories of relativity was Albert Einstein. The special theory of relativity predicts that the speed of light is constant for all observers. This means that light always travels at the same speed towards you as well as away from you, regardless of your own velocity. The famous formula E = mc² states that energy and matter are different aspects of the same thing. Einstein postulated in his special theory of relativity that there is a relationship between the mass of a particle and its energy, and that the mass of a particle increases at very high speeds. That is why, according to the special theory of relativity, it is impossible to travel at the speed of light, since approaching the speed of light would result in that object's mass approaching infinity, which would in turn require an infinite amount of energy to accelerate that object to the speed of light. The general theory of relativity states that space and time are part of the same fabric called spacetime. It then states that objects bend spacetime by an amount depending on their mass, and that gravity is the result of this bending of spacetime, causing other objects to fall towards them. Today we have a great number of experimental proofs for the reliability of general relativity. It now ranks as the most exhaustively tested and best proven principle in all of physics. Today, general relativity reliably describes cosmic dynamics to more than 15 places of the decimal. The final area of physics we take a look at is quantum physics. Quantum physics started with atomic theory, where scientists started probing the nature of matter. It states that matter is composed of discrete units called atoms. Since scientists first started studying the atom, more and more detailed models and descriptions were developed for the atom, from a tiny sphere, to electron orbits, to energy levels, and then to electrons being charged wave-like distributions. Nuclear physics describes the atom's nucleus, what it is made of and how it behaves and interacts. It explains radiation and what happens when you split a nucleus, or force several nuclei together to form one larger nucleus. The process of splitting a nucleus into two smaller nuclei is known as nuclear fission. It is fission which drives our nuclear power plants. Forcing several nuclei together to form one larger nucleus is known as nuclear fusion. At the center of our Sun, fusion takes place, and it is that process that provides the Earth with energy. Scientists are working to harness nuclear fusion here on Earth, since doing so will provide us with almost limitless energy. Condensed matter physics deals with the properties of condensed phases of matter, where many particles cling to each other. Familiar condensed phases are liquids and solids, and more exotic phases include superfluids and the superconducting phase exhibited by certain materials at very low temperatures. Particle physics is closely related to nuclear physics, and it probes very deep to find the fundamental subatomic particles that everything is made of. Current experiments in particle physics include particle accelerators, where particles are accelerated to relativistic speeds and smashed into each other. Doing so creates conditions inside the particle collider resembling that of the Big Bang. Scientists are eager to see what new particles result from such collisions. And that concludes the 3 areas of physics. The next big field we will be looking at is derived from atomic theory, and it is chemistry. Chemistry studies atoms and how they interact with one another. Chemistry can broadly be broken down into 4 areas. These 4 areas are physical chemistry, analytical chemistry, inorganic chemistry, and organic chemistry. Physical chemistry looks at the physics associated with chemical systems. It takes a look at the forces between atoms and molecules, for example, the intermolecular force, which is the force between the atoms of a molecule, and intramolecular force, which is the force between molecules. Then it studies the energy and motion of atoms or molecules in chemical systems. Force, energy, and motion is also very closely related to thermodynamics. The study of forces between atoms and molecules leads to the field of material science. Material science seeks to find new materials with better properties like higher strength and better durability, among others. Most properties of a material are determined by the force between the atoms or molecules within the material. Included in physical chemistry is electrochemistry, which takes a look at chemical reactions that generate an electron flow, or an electron flow from a circuit that causes a chemical reaction. The study of electrochemistry is especially important when designing batteries. Thermodynamics is especially important here since we are dealing with the conversion of energy from one form to another. The next area, analytical chemistry, can be thought of as detective work. It involves the analysis of material samples to gain an understanding of their chemical composition and structure. An older and more traditional technique to discover what a substance is made of is precipitation. It separates compounds depending on what temperature they evaporate at. Modern techniques include mass spectrometry, which separates materials based on their masses when they are moved through a magnetic or electric field. Then there is spectroscopy, which can tell you what materials you are dealing with using optics, and finally, chromatography, which separates compounds due to the different kinds moving at different speeds through a solution. The next area is inorganic chemistry. It mostly studies compounds that are man-made and seeks to find chemicals with new properties that can be used in the chemical industry and in our everyday lives. Examples of inorganic compounds are pigments, used to give the color to paint. And then there are fuels, where chemists seek to create fuels with higher energy to mass ratios for use in vehicles. Another application where there is a lot of research being done is in refrigerants, where chemists try to create refrigerants that are better and safer for the environment. Inorganic chemistry is also closely related to material science, where it tries to create stronger, lighter, and more corrosion-resistant materials. The final area of chemistry is the huge area of organic chemistry. Organic chemistry looks at the molecules which make up living things. Organic compounds are built on a carbon framework. More than any other element, carbon atoms bond to other carbon atoms. There seems to be no limit to the number of carbon atoms that can be assembled into molecules. Some compounds can have carbon chains with millions of carbon atoms in them. The vast majority of all compounds currently known are organic. There is a huge number of applications for organic compounds. Some examples are flavorings for food, polymers for clothing or construction material, lubricants for our everyday machinery, and of course medicine. Organic chemistry leads to biochemistry, which is a study of living organisms, and it studies how they function and how they work. Biochemistry is no doubt a huge field of study on its own. So that concludes all the areas of chemistry. There is still a lot of science we do not know or understand. The most notable areas of ignorance right now lies within physics. Currently, the best description of the universe we have is quantum field theory. It combines a special theory of relativity with quantum physics. Unfortunately, gravity does not currently have a complete quantum theory, and is thus not included in quantum field theory. So scientists don't know how to join together quantum physics and the general theory of relativity, leading to many unanswered questions about the universe. We hope to one day come up with a theory of all of physics, which we call quantum gravity. Attempts to do this include string theory and loop quantum gravity. Some other things we observe but don't understand anything about are dark energy and dark matter. Through observations, dark energy is now recognized to be the dominant component of the universe. It is the energy that is embedded in the space surface of the universe and is responsible for the increasing rate of expansion of the universe. Dark matter is made up of fundamental particles which does not strongly interact with light. This means that dark matter is, you guessed it, permanently dark. Dark matter resides in giant halos around galaxies. Combined, dark energy and dark matter make up about 95% of all the content of the universe. This means that all the matter we are made of, all the planets and stars we can see, only amount to 5% of all the stuff in the universe. There are many more things we do not understand, and no doubt things we don't know that we don't know. That is where philosophy comes in. It is the big philosophical questions that motivate a lot of science. Questions like, what is the fundamental nature of reality? How do we know that the way we do science actually gets to the fundamental truth of the universe? How can mathematics, which is a man-made thing, explain so much of the universe so well? Why is everything the way it is? Those are big questions, and we attempt to answer those kinds of questions on this channel using science. And finally, we move to the field of engineering. Engineering is the application of mathematics, physics, and chemistry to design and build structures and machines and systems to improve and simplify our daily lives. It demands that you have knowledge of all the fields discussed in this video, and it requires quite a bit of creativity. When you first start studying mathematics and science, everything can seem quite overwhelming. But when you keep pushing through, everything will start making sense and you will see the connection between all the fields. Having a good grasp of mathematics and science is very valuable. It teaches a certain way of thinking and problem solving. On this channel, we delve deeply into mathematics, science, and engineering to discover the interesting facts and secrets of the universe. But first, we have to start at the basics. We first need to learn the language of physics before we can attempt to unravel its mysteries. We need to learn mathematics, and that is what we are doing in this series. We are starting at the very beginning. Thank you for watching. I will see you soon, and remember, always stay curious.